Right, so we've got indirect measurement here, which is kind of like a subcategory or extra topic, if you will, from section 4. And I wanted to do this separately because there's 4 different methods that I wanted to touch on that the book doesn't really go into a lot of detail with. So let's take a look at these 4 different methods for actually measuring objects that are too large or too far away for you to actually directly take a ruler or yardstick and measure. You have to do it using similar triangles and take measurements that you can that are reasonable. So let's take a look at the first method. Say you wanted to figure out how tall a house was and you didn't have a ladder. Okay. What you can do is you can take an object, any straight object. It could be a pencil, it could be a ruler, whatever. I'm using a ruler here. And you can hold it in front of your face so that the top of the ruler is right at eye level. And you place yourself so that that top of the ruler matches up with the top of the house when you're sighting it. Okay? So this is kind of the situation. Here's your ruler. You're looking out. You see the top of the ruler matches up with the top of the house. And I know it looks like he's floating above the house, but this is really like he's far away from the house. Okay? What you can do is you can actually measure the distance between your eye and the ruler. You can have somebody measure that for you. And you can measure the distance between the ruler and, say, the base of the house, which should be where the height of the house is. So you can do these measurements on the ground really easily, right? So hopefully you guys can see that there's going to be some similar triangles here. So first of all, if I add in this line, this is the height that I'm looking for. I'm going to call that h. Height is always measured along a perpendicular, so there's these right angles right here. And then this angle right there is going to be the same for the little triangle as it is for the large triangle. So we do have similar triangles, we just have to set up the proportion for. So what we're going to do is we're going to say this, since it's a 1-foot ruler, everything is measured in feet, so this is 1 is to the height here of the height of the house. That's going to be the same as the distance from your eye to the ruler as it is from the distance of your eye to the house. So because this is 2 and that's 50, we had to add those up to get the entire length of 52. So 1 is to h as 2 is to 52. So that means h is 26. So we know that now the house is 26 feet tall. Okay? So that's one method. Here's the next method. The method 2 involves the sun. So you're casting shadows on the ground. So say you had this big tall tree here that was too tall for you to be able to climb up and actually measure, and you want to figure out how tall it is. Well, the sun is high up in the sky. It casts a shadow in front of the tree. And so you can actually measure the length of that shadow on the ground. Okay, so you just take another object, whether it's yourself or a meter stick or a pencil or whatever, and you hold it straight up at a right angle, and it should cast a shadow as well. And so you can measure what that shadow is. So what you have to remember, and this is just a physics thing, the sun always casts shadows at the same angle as long as you're measuring at the same time of day. So say you and your buddy are out there and you measure the shadow of the tree and the shadow of your meter stick. You find them to be 21 meters and 1.5 meters. You know that your meter stick is 1 meter long. Okay, awesome. You want to figure out what the height of the tree is. Because these angles are the same and they're both at right angles, we have similar triangles. So we can come up with a proportion. We can say x is to 1 as 21 is to 1.5. And then we cross multiply and we solve and we get the height of the tree is 14 meters. Okay, so that's really important to do. Now there's a variation to this method too. Still using the sun, okay, still using a second object to figure out the shadow, but it doesn't have to be like placed over here. It could actually be placed inside the shadow of the object you're looking for. So that's what would happen here. So say we wanted to figure out the height of the flagpole. And this person stands herself right in the shadow of the flagpole, just in the correct position that her shadow matches up with the tip of the shadow for the flagpole. So her shadow ends right here, and the shadow of the flagpole also ends right there. So you can measure her shadow is 2 feet 6 inches. She should know her height, 4 feet 2 inches. And then you can also measure the distance between the person and the flagpole, which is 5 feet. Okay, so you have these 3 measurements here that you can use now to figure out the height of the flagpole. And if you see, you do have similar triangles. You've got the big triangle, and then you have the little triangle, this little one right here. Okay, now another little nuance to this, I made it a little harder. This is in feet and inches, and when you go to make your proportion, they all have to be in the same unit of measurement. So we're either going to convert this all into feet or all into inches, and I have to say it's probably going to be a lot easier to convert it all into inches. So let's do that. Okay, so we're going to take the 4 times the 12, add 2, 4 times 2, add 6, and then, I'm sorry, 2 times 12 and add 6, and then 5 times 12, you get that. Okay, so we get the 50, the 60, and the 30. So let's come up with our proportion. We can say x is to 90, which is the shadow of the flagpole, this whole thing. And then we can do the height of the person, 50, to the shadow of the person, which is 30. So we did height is to shadow, height is to shadow. Okay, so we can simplify and cross multiply and divide, and we end up getting that the height of the flagpole is 150 inches. But since the problem gave us these measurements in feet and inches, we should probably put the answer in feet and inches. So to do that, we're going to take the 150 and divide by 12. And we get 12.5. So that means that the flagpole is 12 feet 6 inches. All right, so that's dealing with shadows, whether they're shadows created by the sun or a lamppost or something making light that creates shadows. What happens if you're in the dark? What if it's a cloudy day and there are no shadows? So the method 3 involves mirrors. And so here's another physics lesson for you, is that the light reflecting off a mirror makes equal angles or congruent angles. So when you're looking down at a mirror and you're looking up, like in the mirror, you see the top of another object up here. So it's like, these 2 angles are going to be congruent. And so if you measure the distance above the ground that your eyes are, and you are looking for the height of the flagpole, you just need to measure the distance between the mirror and the flagpole and the mirror and the person that is measuring this. Okay, so we've got 24 feet, 9 feet, and 6 feet. We can set up our proportion. We can do height is to height as shadow is to shadow. Simplify, cross multiply, solve, and we get the flagpole is 16 feet tall. Okay, so that's method 3. Remember I said there were 4 methods, so we got 1 more to go. Here we go. Method 4, finding the distance across a river or a chasm or a lake or something that you can't actually bridge. There's no bridge to cross it to actually measure. You would have to do all of your measurements on, say, one side of your cliff or shore of the lake or river. It involves you taking like these poles, these are poles, these 4 objects here, and string that you would connect with these poles, creating right angles here, and when you sight across, you're looking across, you make sure that this is exactly a 90-degree angle. And when you're sighting this, making the pole there for where you see the tree. You don't need to know the logistics of it, you just need to recognize that there are similar triangles here, right? So we got vertical angles, we got right angles, we're good to go. So we're going to set up our proportion. We're going to do x is to 6 as 10 is to 4. And then when you simplify, you end up getting x is 15, so the river is 15 feet across. Okay, So whenever you're doing these indirect measurement problems, what you're looking for are the similar triangles. Whether you're creating them by doing these measurements, or you're looking at shadows from the sun or a lamppost, or you're using a mirror, or you're just placing yourself in a certain position where you are looking across at the house, somehow, some way you are making these similar triangles in order to set up a proportion to solve for a missing height or distance. Okay, so lots of algebra for those of you that like algebra, lots of calculations, so that should be good for some of you. Sorry for the rest, that's not your thing, but we're almost done.